Hey, you know about physics, right? So what is entropy? Entropy? I think it's like that when I have, for example, a stack of papers and I put the papers everywhere on the ground and that is so messy. That is disorder, yeah, not order. And that is entropy, right? Um, not not really. Entropy is not disorder. I'm sorry, but it's not.
Disorder, what we also call
Entropy.
entropy.
No. So what is exactly entropy? Can you explain that? Alright, let's talk about entropy. In fact, we cannot say the specific combination of the papers here in the stack of paper or on the ground, which one has more entropy or disorder than the other. No. For example, I want to make a film about how messy I am, how lazy I am. So I have to take the paper on the stack of papers, put it in on the ground, yeah, put it everywhere on the ground. And this combination of papers on the ground is exactly what I want, and that is the most ordered combination I can make. So the people say that is disorder, but I say that is the most order. The concept of entropy only applies for the macro state, not for the micro state like that. And there are two different ways to approach the term entropy. The first way, of course, the classical mechanic, and that is about the heat. Yep. In the past, the people used the term entropy to describe or to measure the amount of heat, for example, in my room. And for example, I have here a heater. You can see that? Yeah, heater. Yeah, heater. And if I feel so cold, I can turn on the heater. And of course, you can understand the electricity or the electrical energy is converted to the thermal energy or to the heat. And based on the kinetic theory of gases, this heat around my room is the movement of the small air particle, a small air molecule. Yeah, this small air molecule, they move, they swing or they rotate. And yeah, basically entropy is this heat amount in my room, and the more heat amount, that means the more the particle move and swing and rotate, and the more entropy. And probably that's why the people see, okay, the particle moves so quickly and that is so disorder, and disorder means more entropy. But I would say, yeah, it's only true in this case because you consider the whole system is disorder. You consider the macro state, the system is disorder. So you can say in that case that entropy is disorder in the macro state. Additionally, entropy can be set latently. For example, I still keep turning on my heater, but now I open the door to the hole, yeah. And now the temperature in my room doesn't rise anymore, but the heat in my room is travel from my room through and to the hole. The entropy in this whole system, my room and the hole, increase or rises, but the temperature in my room doesn't rise. So in this case, when the temperature doesn't rise but the volume increases, we call that entropy is saved latently. So from the classical mechanic view, entropy is this heat amount in the system. The more the particle move in the system, the higher entropy. The second way to approach the term entropy is statistic. Now we consider entropy is a measurement like that for the total of arrangement of particles. Yeah, a bit abstract, right? So let's take a look at this example. In the first system, we have 3 objects and only 4 different positions for them. As you can see, we have different combination of them. Now look at the second system. We still have 3 objects, but the number of positions is 16 now. And that's why the total of combinations are significantly increased. We can say the second system has a higher entropy than the first system because the total of arrangement of particles in the second system is higher than the first. So of course, the bigger the size of the area, which is the particle objects, are confined to, the larger number of combinations we have, and also the higher entropy this whole system has. But each combination in microstate is equally likely. We cannot say that this configuration is more orderly than this one. No, they are equally special. And again, we only can use the term entropy for the whole system or for the macro state, not for the specific case. This statistical view of entropy also has something to do with information, because okay, when you have the more volume or the more size to sort this small particle in this size, and we have more combination, and that's why we can save more information. The best example is our computer. The 16-bit has of course 16 places, and we only can put the value in these 16 places 0 or 1. But when we have 32-bit, we have 32 different places, so we can put more differently combination of the number 0 and 1, and that's why we can save more differently data. We can only apply the term entropy to compare two systems. Yeah, in this case, it's the 32-bit has higher entropy than the 16-bit. In this 16-bit, we of course can save differently 0 and 1 different data, and we cannot use the term entropy for this microstate. We cannot say that the chain only 0 has less entropy than the chain with differently 0 and 1 in a system 16-bit. It's not true. That's what two different ways to approach the term entropy. Yeah, we can repeat it one time, that the entropy, we can see it is a heat amount. Yeah, in the system, heat amount, the more it move, the more, of course, the more warm I feel, and it's also the more entropy in this system. Or entropy is also the total or the sum of arrangement of particle, yeah, or the size, the volume to save information. And entropy has a property that it only can be increased, not decreased, in a closed system. Yep. For example, I am in my room, and when I do that, yeah, that we call that is friction process. Yeah, when I do that, I create more entropy, and the entropy is in for information, and heat is only can be increased in my room. If I want to decrease the entropy in my room, I have to use the energy from another system, for example, the people outside my room, and give me energy to decrease my entropy. If we want to decrease the entropy in this system, we have to use energy from the other system. And when we consider this universe is a system, yeah, this whole universe is a system, so there are no energy from the other universe or something, and that's why this entropy in this universe cannot be decreased. And that's also the time arrow, the direction of the time arrow. We cannot travel back time, because in order to travel back time, we have to decrease entropy in this universe, but we can't decrease that with the energy in this universe. Yeah, theoretically, we can decrease the entropy in a system by using the energy from another system. But assuming that we're only in this universe and no more energy outside, and that's why we cannot decrease the entropy, and that's why we cannot go back to the past. Yeah, but of course we can go to the future by traveling fast. The idea of relativity, theory of relativity from Einstein, going fast, and you going fast, you also create more entropy, and this process and this normal process of the people living, these two processes have the same direction, and that's why you can go a bit faster and travel to the future. That's possible, but travel to the back, no, because of entropy. So to summarize, entropy is a heat amount, or entropy is also the number of combination. The more differently combination, the more entropy. Thank you.